Hey everyone, and welcome. So today, we're going to dive into a concept that could totally flip the script on how we think about reusable rockets. It's called motion theory, and it basically asks, what if we stopped fighting the brutal forces of spaceflight and started conducting them instead? So, right off the bat, this is the core idea, the central metaphor for everything we're about to talk about. Stop thinking of a rocket as just a big, rigid metal tube. Instead, I want you to picture it as this giant, complex orchestra. And the goal? It's to land that entire orchestra from space without breaking a single instrument, get it retuned, and have it ready for the next show, super fast. I know, it's a fair question, right? It sounds a little out there. But this mental shift, from using brute force to using elegant management, is what might just unlock truly rapid and full reusability. So, let's really dig into the problem this whole theory is trying to crack. You know, for decades, the whole engineering game plan for reentry has been this brutal war of attrition. You just try to build something strong enough to survive the absolute beating that nature wants to give it. But that approach, well, it has its limits. I mean, just think for a second about what a rocket goes through. We're not talking a little warm, we're talking scorching, plasma-level heat, violent shaking, and stresses that are literally trying to rip metal apart. And even if the thing survives, it comes back battered and bruised and needs slow, incredibly expensive, and painstaking repairs. This, right here, is the bottleneck. This is what makes flying again quickly so insanely difficult. And this is where motion theory just flips the script entirely. It says, hey, instead of building thicker walls to block out all that chaos, what if you could learn to direct it, to manage it, to bring it into sync with the vehicle? To even get there, we kind of need a new language to describe what's really going on. Okay, first up, time. It's not just ticking seconds on a clock anymore. In this world, time is your rate of operation. Winning the game means lowering the retune time for every single part of that rocket. It's all about speed. Next, mass. It's not just how much something weighs. Think of it as resistance, specifically resistance to being retuned. The goal is to design parts that want to return to their original, perfect state after a flight. It's almost like you want them to have a memory, to just snap back into place. Now, this next one, this is a total game changer in how you think about heat. See, in this theory, heat isn't just energy you need to block. It's a symptom. It's a symptom of chaos, of desynchronization. It's what happens when the nice, orderly motion of the system breaks down and leaks out as damaging, random vibrations. And what about gravity? Well, it's not just this enemy you have to fight with raw power anymore. It's an environmental gradient. It's a force you can actually align with, using its pull to guide your path in a way that's way more efficient and a lot less stressful on the vehicle. And when you put it all side by side like this, wow, the whole paradigm just shifts right in front of your eyes. You go from fighting stress to managing sink, from blocking heat to directing flow, from resisting gravity to aligning with it. And, maybe most important of all, you get out of the cycle of damage and repair and into a rhythm of rapid retuning. All right, so that's the big idea. But how did this actually work in the real world? How do you do it? Let's get into the playbook and look at a few of the actual levers you could pull to tune this rocket orchestra. First step, and this one is just so clever, is how you deal with heat. Instead of just building a thicker, heavier heat shield, what if the rocket's own skin could sweat to stay cool? It's called transpiration cooling. So you take the tiny bit of propellant that's going to boil off anyway, and you bleed it through these microscopic pores in the steel skin. What that does is create this super thin layer of cool gas that acts like an invisible, self-healing shield, pushing the worst of that reentry plasma away. It's a perfect example. You're adding a little bit of controlled motion to keep the bad, chaotic motion out. Next up, stability. So picture this. A massive rocket coming in hot, at a crazy angle. The forces on its fins are just immense. The old way? Just build them stronger, heavier. The new way is way more elegant. It's called vortex scaffolding. You use these tiny puffs from the control thrusters to intentionally create swirling vortices, literally like smoke rings, that wrap around the body of the rocket. And what you're doing is trading a tiny, tiny bit of drag for a massive gain in stability. These vortices act like an aerodynamic cushion, taking the pressure off the actual mechanical parts and just keeping the whole vehicle flying straight. Okay, So we've landed. Now comes the real bottleneck for reusability, the inspection. How in the world do you find microscopic cracks or hidden damage without spending days or even weeks taking the rocket apart? You give it a health checkup with lasers and sound. It sounds like something out of science fiction, right? After landing, you use this technique called laser vibrometry to get a frequency fingerprint of the whole vehicle. See, every part has its own unique vibrational signature when it's healthy. If that signature changes even a tiny bit, it's an instant red flag that there's a hidden crack or flaw somewhere. What used to take days of people crawling all over the vehicle could now take just minutes. All right, so after all this clever new thinking, what's the score? What does this actually get you? Well, the projected numbers are what make this whole theory so incredibly compelling. This isn't just an academic exercise. It's all aimed at hitting some very specific game-changing results. First, a potential 10 times reduction in losing heat shield tiles. Just by managing the flow and heat better, that is just a massive drop in repair work right there. And with tech like that transpiration cooling we talked about, well, tests suggest you could knock down the peak heat hitting the rocket in those spots by as much as 30%. You're not just taking the hit, you're actively pushing the heat away from the structure. And here's the big one for getting these things flying again fast. Using things like those vibrospectral health checks could slash the manual, hands-on labor hours needed after a flight by up to 60%. 60! That's huge. And all of these levers, all of these clever ideas, they all point to this one single, absolutely audacious goal: turning a rocket around from the moment it lands to its next launch in less than 24 hours. So, when you boil it all down, it's about this one simple idea: motion hygiene. It's about keeping the system clean, synchronized, and orderly. It's about creating this beautiful, repeatable rhythm of fly, land, retune, and repeat. And that really leaves us with this powerful final thought. Maybe, just maybe, full reusability won't be won by building an invincible rocket that can beat the forces of nature. Maybe it will be achieved by building a smarter rocket, one that understands the music of motion, and finally learns how to conduct the orchestra.